Hello, Algebra 2. Here is the start of our second week on rational functions. I know these presentations have been long, and I'm sorry, but this week is going to be the same way. Like I said, this is one of our most difficult units. Anyway, this first screencast, we're going to try to explain to you how to find a horizontal asymptote. And once we do that, then we'll be in a position to start talking about, talk some more about how to sketch rational functions. So with that, join me on slide 2 and let's get into it. So here are 4 rational functions that we showed you at the end of last week's presentation. And if you have a graphing calculator, or if you'd like to go to desmos.com, I'd like you to take a minute and just graph each one of these rational functions and see if you can notice where the horizontal asymptote is, if there is one. So pause the presentation, take some time and do that. And then when you think you have the answers, join me on slide 3 to see if you got them right. Okay, so hopefully you didn't have any trouble doing that, and you notice that there are differences in the horizontal asymptotes, at least some of them. Number 1 and number 3 appear to have the same horizontal asymptote, but number 2 and number 4 have different ones. So now that we've noticed those differences, let's see if we can try to help you understand why the horizontal asymptote is in a different location on some of these functions. The one thing I want to remind you before we get into this is one thing you definitely don't want to do. Some people still try to look at these and think of them in terms of transformations. Some people want to look at this number here hanging on the end and say, oh, you're subtracting 6, so the graph must move down 6. Well, obviously, that's not right because you can see the asymptote is not at -6. The couple things I'd point out to you, first of all, we're not doing transformations anymore. Second of all, you should be, if you were doing a vertical transformation, that -6 should be outside the function. Outside the function would be outside the fraction, and your -6 is clearly inside the fraction. Second thing I could point out to you is, well, you have a -6 down there, but what about the -1 up here? So if you're trying to do transformations, how do you decide which one of these numbers is the one you should pay attention to? So again, just you have to remember we are not doing transformations anymore. We're giving you a totally new way of understanding rational functions. So with that, let's dive into the explanation on slide 4. Okay, so I think it was back in the unit on cubic functions where we might have mentioned this idea of end behavior. Horizontal asymptotes are a type of end behavior. And one of the things you have to understand is end behavior is concerned with what happens on the far right end and the far left end of the graph. That's why we call it end behavior. Now, the right end of the graph, if you're on the far right end of the graph, you're going to have really big positive x values. So you're going to be approaching positive infinity. But if you are on the left end of the graph, then you have to have really big negative x values. So then you would be approaching values like negative infinity. So that's one of the things that you need to understand about horizontal asymptotes. We're really just talking about the far right and the far left side of the graph. That being said, another thing that you hopefully remember is what the degree of a polynomial is. If you want to understand the horizontal asymptote for a rational function, then the first thing you have to do is you have to look at the degree of the numerator and the denominator. The degree is nothing more than the highest exponent. So if you understand what the degree is, let's go back and look at those 4 problems and see if we can dissect how to find the horizontal asymptote. Okay, so there's basically 3 different possibilities or 3 different rules for horizontal asymptotes. Here's the first one. It says if the denominator has a higher degree than the numerator, the asymptote will be 0. Okay, well, we know that we have two functions where the asymptote is 0. So let's see if we can understand why the asymptote is at 0. Take a look at the first example. Remember, degree is highest exponent, and I hope you realize that this x, if I wanted to, I could put an exponent of 1, and that's why we would consider that denominator to be first degree. Now, what about the numerator? It doesn't even have an x. So what's the degree of the numerator? Well, I'd like to point out to you that it doesn't have an x, but if you wanted to, you could put an x there provided you had x to the 0 power. Because what's x to the 0 power? Well, anything to the 0 power is 1. So that's why you're allowed to write x to the 0 power there, because you're just multiplying by a 1, which doesn't change anything, right? So now when you look at that function, I hope you can see that, okay, the numerator is 0 degree, and the denominator is first degree. And like the rule says, if the denominator is a higher degree, then the asymptote is 0. Look at example 3. This one's a little more straightforward. Again, this x, if I wanted to, I could put an exponent of 1 there. So clearly this is a first degree, and the bottom is clearly second degree. And since the bottom is higher degree, that's why the asymptote is at 0. So anytime you have a rational function where the bottom is a higher degree than the top, the asymptote is going to be y equals 0. Here's the next rule. This one's a little more complicated. It says if the denominator and the numerator have the same degree, then the asymptote will be y equals n over d. N and d are the coefficients of the numerator and the denominator. So that's a lot to digest. Let's see if we can break it down. First, let's focus on, do you have the same degree? That's the first thing we have to worry about. Do you have the same degree? Okay, well, problem 2 is that would be x to the first power, and this would be x to the first power. So yes, those are the same degree. They're both first degree. All right, that means we need to look at the coefficients. I'm going to change colors here. So the coefficient is the number in front of the variable, and it looks like there is no number in front of the variable. Well, once again, remember, you can always multiply by a 1, so we would say that that coefficient is positive 1. But down here, because you're subtracting, when I put a 1 there, that means your coefficient is negative 1. So the coefficient in the numerator is 1, and the coefficient in the denominator is negative 1. And you can see that 1 divided by negative 1, that's why your asymptote is at negative 1. If we jump down to problem number 4, you can see that the top is second degree, the bottom is second degree. So once again, the degrees match. This has a coefficient of 1. This also has a coefficient of 1. Therefore, your asymptote is going to be 1 over 1. And that's why this asymptote is at positive 1. Okay, our third and final rule, and probably the easiest one. There was no example of this in the 4 problems that we were just looking at. It says if the numerator has a higher degree than the denominator, there will not be a horizontal asymptote. Now, to illustrate that, since that didn't happen in any of the 4 previous examples, here's 3 new examples that you can look at if you want to. So I'm not going to work these out. I'm just offering them up in case you're curious. Again, if you have a graphing calculator or Desmos, if you take the time to graph each one of these functions, I hope when you see the graph, you'll be able to confirm that there is no horizontal asymptote on any one of those graphs. In fact, just as a little footnote, I'd like to point out to you that that first function, that technically is not even a rational function, because what you've got there, x plus 4 divided by 2, well, that's x divided by 2 plus 4 divided by 2. So in other words, you just have 1/2 x plus 2. That's just a linear function. It has a slope of 1/2 and a y-intercept of 2. So that definitely doesn't have a horizontal asymptote. Anyway, I'll leave it to you if you want to look at those graphs and confirm that there's no horizontal asymptote. That's horizontal asymptotes. So now let's transition to how do we take all this information plus the information we gave you last week and start working on sketching graphs of rational functions. So before we do that, I just want to remind you something that we told you last week. Keep in mind when we graph rational functions, we don't have really high expectations for how accurate your graph is going to be. The things we are mostly interested in are make sure you show the asymptotes and show them with a dashed line. You should try to locate the x and the y intercepts. Oftentimes those numbers might be fractions, so you may not have nice round numbers that you can plot accurately. So just do the best job that you can showing the intercept as accurately as possible. And then we want the general shape of the graph to be correct. In other words, by general shape, if a graph is supposed to approach the asymptote, then you should show something that's getting closer to the asymptote. And when it comes to vertical asymptotes, obviously, if the graph is going up, we want to see the graph going up, not going down, and vice versa. There is one other thing I'd add to this list based on what we learned last week. Now that you know what a point discontinuity is, if you have a point discontinuity, you should show that point discontinuity with an open circle. We explained to you last week that graphing calculators don't really show point discontinuities because they're so small, they're single points. But when you draw a graph, we want you to use an open circle to show us that you understand there is a point discontinuity. So we'll demonstrate all this with some examples here to wrap up the slideshow. Okay, so we're going to go through all 5 of these examples, which is going to take some time. So I don't know if you would like to pause the slideshow, write these down, and try them on your own, or if you just want to click through the next few slides. But basically, the next 5 slides are going to be me demonstrating how to graph these 5 examples. I'd like to tell you right now that your assignment this week is going to involve graphing rational functions like these. So you should really pay close attention to the next 5 examples to get some tips and some advice on how you should go about doing your assignment for this week. Okay, so here's the first problem. On each of these problems, what you're going to see is that I'm going to always try to answer the same 5 questions. We want to know, well, let's start with today's information. And I'm going to abbreviate HA for horizontal asymptote. We're going to try to figure out where's the horizontal asymptote. We're going to try to figure out where's the vertical asymptote. We're going to try to figure out, do you have any holes? And then we're going to try to figure out, do you have an x-intercept and do you have a y-intercept? And if I can answer those 5 questions, that will hopefully give me enough information to sketch this graph. So on this function, notice that the top is 0 degree and the bottom is 1st degree. Since the bottom is a higher degree, I know that my horizontal asymptote is going to be 0. My vertical asymptote, that always occurs when the bottom is 0 and the top is not. The bottom is going to be 0 when x is -3. And the top definitely will not be 0. So you do have a vertical asymptote, which means you do not have any holes. Point discontinuities, holes, that happens when the top and the bottom both equal 0. Your top can never equal 0. That means there's no way you could ever have a hole because you can never have 0 on top and bottom. By the way, that means you don't have an x-intercept. To have an x-intercept, you'd have to have a y-coordinate that's equal to 0. For the y-coordinate to be 0, once again, the top of the fraction would have to equal 0, and that's impossible. So this has no x-intercept. Y-intercepts occur whenever x is 0. If you would substitute x is equal to 0, you can see that my y-intercept is going to be 1 over 3. So now I have enough information to start drawing this function. First thing I would do is draw the asymptotes. My horizontal asymptote is basically the x-axis. So even though it's right on top of the x-axis, I'm still going to try to draw a dotted line there just to remind us that that's a horizontal asymptote. The vertical asymptote is at -3. So here's my vertical asymptote. Now I don't have any holes, don't have to worry about that. I don't have an x-intercept, so I should never be crossing the x-axis. And my y-intercept is 1/3, which is, here's, where it's hard to draw this accurately. So as long as you draw a dot somewhere between 0 and 1, we're going to say that's accurate. You definitely don't want to draw the dot between 1 and 2 because 1/3 is not greater than 1, right? So there's the x-intercept. All that's left now is to sketch the graph. Now, here's where you have to think a little carefully. I would say start with the dots. Start with the points that you know. Let's start with that dot and let's move to the right. Now remember, you have a horizontal asymptote, and that's end behavior. So as you go farther and farther to the right, this graph should be getting closer and closer to the horizontal asymptote. Now that's hard to draw accurately, so you just do the best that you can. Now, what about when you go from the dot towards the left? Well, you have a vertical asymptote and you can't touch that line. The question is, should the graph go up or should the graph go down? Well, it can't go down because if it went down, you would cross the x-axis. And if you cross the x-axis, you would have an x-intercept. You don't have an x-intercept. That means you can't cross the x-axis. Well, that pretty much means this graph has to go up. There's no other direction it can go since it can't cross the x-axis. Now, where's the rest of the graph? Well, here is where things get a little vague. And you have to approach the horizontal asymptote when you go farther to the left, and you have to approach the vertical asymptote when you approach -3. So I'm going to just tell you that the graph does this. Now, how do I know that that's right? Because to be fair, and I'm going to change colors here, to be fair, how do I know that it should be the red graph and not the blue graph? Well, I don't. The only way I would know the difference between the red graph and the blue graph is to say, well, is my y-coordinate negative or is my y-coordinate positive? So to decide, is it the red graph or is it the blue graph, you might want to just say, well, let's plug in an x value that's somewhere to the left of -3. For example, let's plug in -4. Well, if you plug in -4, you can see that you're going to get a negative number. And if you have a negative y-coordinate, then your graph should be going down. Now, you can see that the y-coordinate I get is actually right here. So my sketch is not terribly accurate. I guess my red graph should have looked a little more like this. But that's where, again, we don't care. We're not going to critique you too much about which one of those red graphs is right. As long as you don't draw the blue graph. It's definitely not the blue graph because the blue graph has positive y values. So as long as you draw me either one of those red graphs, we're going to say that's good enough. All right, let's take a look at the next example. Okay, so once again, we're going to start by answering these 5 questions. Where's the horizontal asymptote, the vertical asymptote? Do you have a hole? And what are your intercepts? Okay, the horizontal asymptote, the top and the bottom are both first degree. Since you have matching degrees, you have to look at the coefficient. And since the coefficients are both 1, this horizontal asymptote will be at 1. Vertical asymptote is where the bottom equals 0 and the top is not. So you can see that the bottom is going to equal 0 whenever x is 2. And when x is 2, the top will not be 0. The top will be 4. So that means I definitely have a vertical asymptote, and I don't have a hole. There is no number that makes the top and the bottom both equal to 0 at the same time. So you do not have a hole. Your x-intercept is going to be wherever your y-coordinate is 0. My y-coordinate will be 0 whenever my top is equal to 0. So that means -2 will be my x-intercept. And then my y-intercept will be whenever you plug in a 0 for x. So if you plug in a 0 for x, you can see you get +2 over -2, which means your y-intercept is -1. Okay, we should be ready to sketch. Let's draw the horizontal asymptote first. That's y equals 1. My vertical asymptote is x equals 2. My x-intercept is -2, so I should pass through this dot right here. My y-intercept is -1, so I need to pass through this dot right here. I do not have any holes, and so now I have to sketch. Okay, again, start with the dots. You've got 2 dots here, so I hope it's a little easier to see now that, okay, your graph has to connect these 2 dots, right? And since I have to approach the vertical asymptote, it already looks like the graph is pointing down. And yeah, it has to go down, because if it went up, it would cross the x-axis, and I don't have an x-intercept that has over a positive x value here. So the graph has to go down. Going to the left, that's your end behavior. Remember, you've got to approach the horizontal asymptote. So it looks something like that. Now, what about the rest of the graph? Once again, to be fair, I'm going to say, well, it could be this. You could approach the vertical and approach the horizontal asymptote that way. But it could also be this. Now, actually, I say it could be this, except notice what just happened here. If that blue graph was going to approach the horizontal asymptote, at some point it would have to cross the x-axis. And that would mean I have an x-intercept. I do not have a second x-intercept. So you should already know that it's impossible for the blue graph to be right. It has to be the red graph. But once again, if you wanted to confirm your suspicion, you could just plug in a number that's to the right of the vertical asymptote. So let's plug in a number like 4. When you plug in 4, what do you get? Well, 4 plus 2 and 4 minus 2, that's 6 over 2. You get a value of 3. So your graph is right here, and you can see, hey, I actually did a better job this time of sketching the graph. So it's definitely the red graph. It cannot be the blue graph. Let's move on to the next example. Okay, so if you haven't noticed, our examples are getting a little more complicated each time. Start with answering these 5 questions. Okay, your horizontal asymptote, these are both first-degree polynomials. You have a coefficient of 2 on the top, you have a coefficient of -1 on the bottom. And that means your horizontal asymptote is going to be 2 over -1, or y equals -2. Your vertical asymptote, that's when you divide by 0. If x is 4, you will divide by 0. And when x is 4, the top is not going to be 0. So that means you do not have any holes. Your x-intercept is where you have a y-coordinate of 0. To have a y-coordinate of 0, this would have to be 0. So when will 2x minus 3 equal 0? Well, that would be when x is 3/2. So have to do a little work there to figure out my my x-intercept. And my y-intercept is when x is equal to 0. If you plug in 0 for x, you can see that my y-intercept is going to be -3/4. Okay, we're ready to sketch. Here comes the horizontal asymptote. Here is the vertical asymptote. You have an x-intercept of 3/2. That would be right in between 1 and 2. And you have a y-intercept of -3/4. That would be in between 0 and -1. Once again, I have 2 red dots, so I know the graph has to connect, and I hope you can see that this looks like it's headed up. Clearly it can't head down because that would cross the x-axis again, and I don't. And clearly I have to approach the horizontal asymptote. On the other side of the graph, I don't have any points, so once again I'm left with this decision of, well, does my graph do this or does my graph do this? Well, here you go again. I hope you notice, well, you can't do that because you would be crossing the x-axis, so it can't be the blue. It's got to be the red. And once again, you could test it by just plugging in a value of x that was to the right of 4. So if you plugged in something like x equals 6, plug in something like x equals 6, hopefully you'll calculate a y coordinate that's a negative number, and that'll confirm that we have the correct red graph. Okay, I know it's been a long presentation, but now we're really getting to the challenging one, so I hope you've sticking with me here. Horizontal asymptote. Notice that the top is first degree and the bottom is second degree. That means since you have a bigger degree on the bottom, that means your horizontal asymptote is going to be 0. Now, vertical asymptotes. Vertical asymptotes are when the top equals 0 and the bottom, when the bottom equals 0 and the top does not equal 0. Now, look at the bottom, that's quadratic. When will it equal 0? We told you the other week you might need to review your factoring because that's really going to come in handy. That bottom factors into x plus 3 and x minus 3. So I hope you can see that there are 2 numbers that will make the bottom 0. +3 and -3 will both make the bottom 0. Okay, if I plug in a -3, -3 will make the bottom 0, and -3 will make the top equal to -6. That means it's a vertical asymptote. So -3 is a vertical asymptote. But notice what happens when you plug in +3. If you plug in +3, the bottom equals 0, but the top also equals 0. Because you get a 0 on the top and the bottom, that's not a vertical asymptote, that is a hole. So here's our first graph that has a point discontinuity, and the point discontinuity is going to occur at 3. Okay, my x-intercept. Now this is a little tricky. The x-intercept is where your y-coordinate equals 0. And for the y-coordinate to equal 0, the top would have to equal 0. Well, that would appear to be 3. 3 should be the x-intercept. But you just said we have a hole at 3. So how can the graph cross the x-axis at 3 if the graph doesn't exist at 3? So you don't have an x-intercept because where your graph should be crossing, there is no graph. So be careful with that one because I know that that came up on last week's homework and that stumped a few people. How about the y-intercept? Well, the y-intercept is when x equals 0, and if you plug in x equals 0, you can see that you get -3 over -9, which means your y-intercept is 1/3. Okay, so what does this graph look like? You have a horizontal asymptote at 0. You have a vertical asymptote at -3. You have a hole at 3, but don't draw that yet because you don't know where the y value of the hole is. You don't have an x-intercept, and you have a y-intercept of 1/3. Well, 1/3 again is hard to draw accurately, but it's approximately there, somewhere between 0 and 1. Okay, so start with the point. This graph has to go this way to approach the horizontal asymptote. As I go to the left, I have to decide, does my graph go up or down? I hope you realize you cannot go down, because if you go down, you would cross the x-axis, and that would be an x-intercept. You don't have an x-intercept. So that means that this graph must go up. Now, the other side, once again, we're faced with this decision of, how do I know if the graph goes this way, or maybe the graph goes this way? Well, now the only way to know that would be to plug in an x value. So if you were to plug in x equals -4 or x equals -5, I hope you would see that you get a negative y value. And since you get a negative y value, it has to be the red graph, not the blue graph. Now, the only thing we're missing here is the hole. The hole was supposed to be when x equals 3. So I can't do this on the PowerPoint, because if I try to erase, it's going to erase the whole slide. When you do your graph, what we would want you to do is we would want you to take out your eraser and erase the spot on the graph where x equals 3, and then come back and draw an open circle. So I drew a circle here, but my circle is not an open circle because it has a line going through it. So hopefully when you draw your graph, you can erase the graph and draw a true open circle. And so that's what the whole should look like when you have a graph as a whole. And just draw an open circle at a correct x coordinate. We're not going to worry about the y coordinate of the whole. Okay, one final example, and then we'll be ready to wrap things up. Here's our last example. Again, we will start with the same 5 questions. Look at the degree of the numerator and the degree of the denominator. You hopefully notice that the numerator has a higher degree, and since it does, that means you do not have a horizontal asymptote. Vertical asymptotes. When x equals 1, you would be dividing by 0, but look at the numerator. If you didn't factor it, maybe you should. That numerator is x minus 1 times x minus 1. So when x is 1, you will be dividing by 0, but the top will also be 0. That means you don't have a vertical asymptote. There is no vertical asymptote, but you do have a hole. When x equals 1, the top and bottom are both going to be equal to 0. So there's no horizontal asymptote, there's no vertical asymptote, there's only a hole. Okay, well, what about the x-intercept? And the x-intercept is going to occur when the y-coordinate is 0. That means we need the numerator to equal 0. The numerator will equal 0 when x is 1. But you just said we had a hole at 1. So once again, how can you have an x-intercept where you don't have a graph? Okay, how about the y-intercept? Well, if you plug in the y-intercept, if you plug in x equals 0, you'll see that you get 1 over -1, and so your y-intercept is -1. Okay, so what do we have here to graph? We don't have a horizontal asymptote. We don't have a vertical asymptote. We have a hole, but you shouldn't draw the hole right now because you don't know what the y-coordinate is. You have no idea where your graph is. You have no x-intercept. All you have is a y-intercept of -1. Now, how in the world are you supposed to know how to draw this graph? Well, um, you're going to have to take my word for it, and hopefully by the time you watch the next screencast, you'll feel more comfortable about this. But I'm going to tell you that this graph looks like this, and it's got a hole at +1. So there's my graph. It has no horizontal asymptote, no vertical asymptote. It does have a hole when x is 1. Because of the hole, that means it doesn't have an x-intercept because it's not really touching the x-axis. And it has a y-intercept of -1. So I hope you can see that my picture matches all the things that we said over here. You may not understand how I knew how to draw that picture. You're just going to have to trust me. You'll hopefully understand better once you watch the next screencast. But this one's already been long enough, so we're going to wrap things up and let you take a break, and we'll have one more screencast for you to watch that will hopefully help you understand why this graph looks the way it does. A couple final notes. Hey, I don't know if you noticed this, but if you go back and look at the first problem that we did and the fourth problem that we did, you might not have noticed it because I was sketching the graph by hand. But if you get out a graphing calculator or Desmos, I think you'll hopefully notice something interesting. And I'm going to use a graphing calculator to make it a little more clear to you. Here's a table of values for problem number 1. Notice we have an error at -3 because -3 makes us divide by 0, right? But also notice what happens when you get close to the -3. You start to get these really big y values, and that's a sign of your vertical asymptote, right? Well, did you realize that the graph of number 4 does exactly the same thing? It definitely has an error at -3 because you're dividing by 0, but it also has a vertical asymptote. And not only does it have a vertical asymptote, but notice it has the exact same y values, the exact same y values as the graph of number 1. What about when x is 3? When x is 3, this graph has an error because you're dividing by 0. But that's not a vertical asymptote, that's a hole. Notice what happens when you get close to the 3. You're not getting huge y values. That's why 3 is a hole, not a vertical asymptote. Well, again, notice on this function, you get the exact same y values when you get close to 3. But the difference is when you get to 3, this does not have an error because you're not dividing by 0. So what I'm trying to show you on these tables, what you may not have noticed because I was sketching the graph by hand, if you actually look at the graph of these two functions, they are almost identical. I say they're almost identical because you have to remember that this graph has a hole at x equals 3. And remember, graphing calculators don't show you the hole. If I was drawing it by hand, I would draw an open circle right there where x is equal to 3. Except for that one little open circle, every other point on these two graphs is absolutely identical. And that kind of gets to what we'll be talking about in our next screencast. So I just wanted to point that out to you now. One final bit of housekeeping before we wrap things up. You may recall way back in the unit on exponential functions when we first told you about asymptotes. This is the slide I gave you. And I told you that our definition of an asymptote was not technically correct. It was a somewhat simplified definition. Well, because I just couldn't live with myself if anybody thought I lied to them or deceived them, This is why I wanted to go back and clear up this little misunderstanding. See, on the next slide, we will talk some more about horizontal asymptotes. As we said in the beginning of this slideshow, horizontal asymptotes are about end behavior. End behavior means what happens on the far left and the far right end of the graph. If you have a horizontal asymptote, you can't touch the asymptote when you're way out on the left side and way out on the right side of the graph. But if you're in the middle, it's okay to touch the asymptote. Now, you haven't seen a situation involving this yet, but here's an example of a rational function to show you what I'm talking about. If you look at this graph, I hope you notice that there is a horizontal asymptote, and it is the x-axis. So here's where the graph is getting closer and closer. Here's where the graph is getting closer and closer, but it's never going to touch the x-axis when you go far to the left and far to the right. But look at what's happening right here. Right there is the x-intercept. So this is an example of a function that actually crosses the horizontal asymptote. And even though it is touching the x-axis, we still consider the x-axis an asymptote. So that situation hasn't come up in any examples that we've shown you, and I don't think we're going to give you any problems where it will come up. But again, I just wanted to clean up that little bit of, I wanted to clear up that definition that we had given you months ago, and we had warned you it was a somewhat simplified definition. So now you know the real story about horizontal asymptotes. Okay, so I hope after this very long presentation you have some sense of how to find the horizontal asymptote. There's, remember, 3 different rules. One, they all depend on the degree of the numerator and denominator. If the numerator has a higher degree, you have one rule. If the denominator has a higher degree, you have another rule. And if they have the same degree, you have a third rule. And then the last thing we did was walk you through several examples showing you how to put together all the information from last week and this week to start sketching rational functions. Your assignment this week will involve sketching. Before you try to do it though, I suggest you take a little break because this has been a very long presentation. Take a break, then watch the second screencast. I promise it's much, much shorter. And after watching that second screencast, it will help explain one final thing we need to talk about this week that'll hopefully help you fully understand how to sketch. And then we'll tell you what the assignment is at the end of that second screencast. So again, sorry for the very long presentation. Like I said, this is our most challenging unit of the year, but we are definitely in the home stretch now, guys. There's just one more presentation this week and one more week of information for you to get through next week. So hang in there. Good luck.